Welcome to this video for MCET 450 Advanced Mechanics. In this video we're going to review the basics of static system analysis. The problem we have in front of us says, to facilitate shifting the position of a lifting hook when it is not under load, the sliding hanger shown is used. The projections at A and at B engage the flanges of the box beam when a load is supported and the hook projects through a horizontal slot in the beam. Compute the forces, these would be reaction forces, at A and B when the hook supports a 300 kilogram mass. So where we start with all these statics problems is a free body diagram. So we're going to redraw the diagram of the portion that we're interested in, which would be the sliding mechanism here. And we're going to draw it in such a way that we can show the forces that are both applied to it and the reactions those forces generate. So for that, at a minimum, I recommend that you use graph paper. Engineering graph paper is preferred. And draw your sketch roughly to scale, and at a minimum, use a straight edge. If you want to use other tools like a compass or a circle template, you may. So, as I mentioned, you want to draw this roughly to scale. And for that, what you want to do with your graph paper is figure out what the scale needs to be. So, this object here shows that we have a 400 millimeter distance from here to here and 600 millimeters to the next point of interest. Effectively, that's 1 meter. We can say this is 0.4 meters and 0.6 meters. And we definitely want to work in the base units, and we'll talk about that more in a moment. So what we could do is let each one of these squares on our graph paper, the small squares, represent 0.1 meters, and then a big square would be 0.5 meters, and then 2 squares along the graph paper would be 1 meter. So let's set it up that way. So if we look at how this goes, we have this point where the hook is applied, and that's going to be our starting point. We'll call that 0 for all intents and purposes. And what we can do with that is we can make a mark on our graph paper right here. That's where we'll call the 0 point. Now if we go over 4 boxes, and we know that it's a bit down, and we can estimate this, we don't have to measure this out. We can say that point A is right here. And then we know from the origin, if we go over 0.4 plus 0.6, that's 1. So all the way over here is where point B would be from the origin. And we know it's up a little bit from the origin. We'll just guesstimate it to be right about here. Now what I'm going to do is take my circle template and draw some radii. So we'll use this one here. We have a kind of a nose type arrangement here. We'll just kind of guesstimate that it goes like that. And then point A, it kind of projects this way from the bottom. And then point B projects up and touches the inside flange of that box beam. So now we have something that looks like this. Now we can connect the dots, so to speak. Go from here to here. Going to the tangencies of the circle, or the quadrants as the case may be. There, and we know that it extends a little bit past point B. We'll go over here. And now we can go down here. Not perfectly straight, that's okay. And then over here back to point A. Now let's label our points. We'll label them inside so that we can easily draw arrows on the outside, A and B. Now that we have our diagram of the object we're going to be analyzing, we're going to apply any forces or reactions that occur because of those forces to the body. The only one we're told about is this one. So it is going down, right, according to the image. It's got a hook. Down, and a load is attached that is equal to a mass of 300 kilograms. Now, before we go too much further, we should establish our coordinate system. That over here. So, here we'll call this the x-axis and the y-axis, and then the positive direction is the direction of the arrowhead, and the opposite direction is negative. So right now we know this force, and of course this is a mass right now, we're going to have to convert it to a force, but we know that this force is going in the negative y direction. Because of that, we know we have to support it with at least one positive force in the y direction. Now, either A or B are going to have the positive force. We don't necessarily know which one, so we can guess. Now, I'm going to guess correctly, and I'll tell you why it's correct, that we have an upward force, or a positive y force at A, and we have a negative force at B. Okay, we have it. Now the reason for that is if we look at the moments, we know that they have to balance each other out. So if I took moments about point A, my compass here so we can kind of swing this. If I were to take moments about point A, and we know there's a load right here from this 300 kilograms, it would try to rotate the body in a counterclockwise direction around point A. So B has to negate that. So if we're still taking points about point A, but we look at point B, where that goes, B would have to be going in the opposite direction and cause a clockwise moment, which is why B has to be pointing down. By the same token, if we were to take moments about point B, let's look at that. A little bit bigger. So now about point B, the 300 kilogram load is resulting in a counterclockwise rotation. So A has to therefore counterbalance that rotation. So it has to go clockwise. So that's how we know we have these arrows in the right orientation. When you get more complicated models that have multiple forces and reactions, a lot of times you end up guessing and you allow yourself to go through the equilibrium equations, and if you get a negative answer, you know that you have got an error and you got to switch direction. And oftentimes when you get into three-dimensional static analysis, it can get very complicated and you have to go back and redo all your equations. So the more complicated ones, we'll likely use a tool like MATLAB to figure out what the results of the equilibrium equations are. Now that we have our forces, we want to put in the locations between the forces and the reactions. So what we can do, draw a line going up here from point A. That will be an extension line effectively. And then we can also do a similar one coming off of the load application point or the origin. And then we can draw some dimension lines. The origin in A and then between A and B. And we'll put these in meters. So taking the 400 meters from the diagram, we will then say that this is 0.4 meters and this is 0.6 meters. Now when we are in the SI system, we want to use the base units for our calculations. What are the base units in the SI system? We want to use meters for length, kilograms for mass, newtons for force or weight. We would also use pascals for pressure or stress. We would use Newton meters for moments and so forth. The reason to stay in the base units is because it keeps everything consistent. And when you're using a tool like MATLAB as a computational software, what you will find is if you mix units, you have kilograms with kilonewtons and megapascals, that'll give your answers will be way off, and you have to put a whole bunch of correction factors in to correct them, obviously. And keeping things in the base units makes it very simple. So that's a reason to do that. If you were in the U.S. customary system, you would use things like, for mechanics, you would use inches, not feet, although technically feet are the base units, but generally you will use inches for mechanics, and you will use pounds force, right, and pounds mass, which we often abbreviate LBF and LBM. For stress, you're going to use PSI. For moments, you're going to use inch-pounds force. Remember, it's always a force creates a moment. Okay, but we're in the SI system here. So now let's take a look at our equilibrium equations for the system. Remember the equilibrium equations, we use a summation sign, right? Sum of the forces in X has to equal 0, right? Or otherwise the body's moving, and we're dealing with static bodies, they're not moving. Sum of the forces in the Y equals 0. And sum of the moments about a given point, we'll, for this exercise, select point B, has to equal 0. And remember, we have to say which direction is positive and which direction is negative for these moments. So convention is that counterclockwise is positive. So we'll go with that. We also want to take our 300 kilograms, which is the mass, and convert that into a force. So if you recall, from Newton's second law, force equals mass times acceleration, which also can be converted to weight equals mass times g, where g is the gravitational acceleration constant. We say g is equal to 9.81 meters per second squared. So if we take the mass of 300 kilograms and multiply it by 9.81, we will get 2,943. That is newtons. That's our base unit for force. So when you multiply the base units of mass and acceleration, you get the base unit of force. And again, that's why you work in the base units. It will help you, keep you from making unit errors. Okay, so what I recommend now is that you pause the video and write out your equilibrium equations algebraically. Write those out. You don't have to solve them, but write them out. And then when you are ready to resume the video, we'll take a look at what I come up with, and you can compare them to your answers. So I'll give you a moment to pause the video. Okay, hopefully you tried to write your equilibrium equations. So now let's write out the solution here and see how they compare to what you came up with. So we know that the sum of the forces in X equals 0. There are no reactions or other forces in X, therefore that just stays the way it is. There's nothing else to write. Then the sum of the forces in Y equals 0. Now I like to start with my positive forces first, so I don't have a negative sign in front of the equation that can sometimes be easily missed. So if we look, we have a reaction at A, and let's label this RA, and we'll label this one RB, so we know what we're talking about. So we'll say the reaction of A, that's positive, obviously. And then from that, we have to subtract the reaction at B, because that's going down. And we also have to subtract the 2,943 newtons. Okay, well, so far we've got one equation with two unknowns. We can't solve that. So you have to keep going. So let's go on to our moment equation. So now the sum of the moments about point B, with the counterclockwise being positive, equals 0. And what does that equal? Remember, we talked about it earlier. So the 300 kilogram load, which results in 2,943 newtons, that's trying to twist counterclockwise around B. So that would be positive, and like I say, I like to put my positive forces or moments first in the equation, so we'll write that out. That is 2,943 newtons, but remember, a moment is force times distance. So what's the distance? For the application of the load from B, it's 0.4 plus 0.6, so obviously that is 1 meter. But make sure you write it out in case you ever go back and look at your equation and you'll be like, where's my distance? What did I do? So write it out so you have it. It also helps with our units when we multiply those together and make sure we have the right units of measure at the end. And then point A, that results in a clockwise moment, so that's going to be negative. And that is 0.6 meters away from point B. So this is going to be minus RA times 0.6 meters. Okay, now we have two equations and two unknowns. We call that a system of equations. If we have this at least the same number of equations as we have unknowns, it is now solvable as a system of equations, also known as simultaneous equations. So we'll start with taking the moment equation and solving for RA. Then we'll put the result of RA into the forces of Y equation and find RB. So might be another good point for you to pause the video and come up with a solution, and then return to the video and see if you get the same answers as I do. Second to pause the video. And now hopefully you're back with some solutions for RA and RB. But we'll go right through this algebraically and try not to skip any steps so that there's nothing lost as we go through this. I used to always hate when my instructors would skip steps, or textbooks will skip a step and you're going to scratch your head. What did he do in the middle of that? So we'll try not to do that. Okay, so first of all, what we want to do is we want to solve this equation here for RA. So the thing to do is to get the variable by itself to have a solution. So we'll add RA times 0.6 to both sides of the equation. Basically, that means this comes onto the 0 side, so we end up with RA times 0.6 meters. Carry your units through to make sure you're getting the right answer. And then that's equal to, now we'll do the 2,943 times 1. So we end up with 2,943 Newton meters, right? Now that's a moment. Can't multiply yet because we still have an unknown variable. Now we will take and divide both sides of the equation by 0.6 meters. 0.6 meters. On this side we have 0.6 minus 0.6. They cancel out because 0.6 divided by 0.6. So, if I saw that minus a minute ago, 0.6 divided by 0.6 equals 1. So RA times 1 is simply RA. But this one we can multiply through 2,943 divided by 0.6. Now look, the meters cancel out and we're left with newtons. And that's what we want. We want our answer in newtons because we're looking for a force. So that means RA equals 2,943 divided by 0.6. And that will give you 4,905 newtons. So now we have RA. Let's move over here and solve for RB. So go back to our sum of the forces in Y equation, and we'll just rewrite that here. So 0 equals RA minus RB minus 2,943 newtons. And now we can plug RA into there, and the equation becomes 0 equals 4,905 905 newtons minus RB minus 2,943 newtons. So now we can add RB to both sides of the equation. So we end up with RB on the left. It cancels on the right. RB equals 4,905 newtons minus 2,943 newtons. Do the math. We find RB equals 1,962 newtons. So now we've got our answer. We know that the value of RB is 1,962 newtons, and the value of RA is 4,905 newtons. Now, why is this important? Well, if we were going to analyze the effect on the box beam, we wanted to see if the box beam was strong enough to support a load of 300 kilograms, we would look at the application of A to the bottom flange and B to the top flange, and then we would analyze the beam to see if it can support those loads. That's it for this example. Thanks for watching.